Dousing ourselves in the perpetuation of the universe, we individuals have persistently investigated the danger of whether we most certainly are the essential species to have a planet looking on the stars, considering distant universes, and exploring the potential for life beyond our little blue planet. That limit has finally arisen. NASA's boss has obviously stated that the James Webb Space Telescope has discovered something extraordinary near the precarious edge of our enormous local area. The James Webb Telescope has no doubt about Proxima B, the closest and most plausible exoplanet to Earth. We explored that a potential town made by intelligent living things was identified, which, up to this point, we don't have the faintest idea about. The new James Webb discovery suggests how the splendor of the artificial lights of the city of Proxima B has advanced in expansion. The synthetic blend of the environmental elements of this exoplanet has been selected so that together with us, we can embark on this high-quality trip to Proxima B to find the subtleties of this discovery. As shown by NASA's boss, the James Webb Telescope might have used this advancement just, and as exceptional presence on Proxima B, an exoplanet found approximately 4.24 light-years from our solar system. Proxima B has transformed into a symbol of hope due to its potential for habitability. This exoplanet orbits its matching megastar, Proxima Centauri, a red dwarf that could be much smaller and cooler than our Sun. Discovered in 2016, Proxima B lies within the star's habitable zone, also referred to as the Goldilocks zone, the region around the star where conditions should allow the presence of liquid water, a basic component for life as far as we are concerned. Proxima B's proximity to Earth and its location within the habitable zone have generated significant interest and speculation about its potential to support life. However, it's important to remember that the habitability of an exoplanet is a complex puzzle, which includes various factors. Proxima B is described as an exoplanet with a mass around 1.3 times that of Earth, and it completes one orbit around Proxima Centauri in about 11.2 Earth days. However, things are not as straightforward as we might expect. The fact that the planet is Earth-like in size and orbits a red star doesn't guarantee that it's a perfect imitation of our world or that we can move there. The habitability of Proxima B is not set in stone, known through various factors. One of them is a planet's atmosphere, which acts as a protective shield and plays a crucial role in regulating temperature and supporting life in general. Moreover, the specific composition of Proxima B's atmosphere is still uncertain, making it difficult to determine its overall habitability. Scientists are working on methods to analyze the atmosphere of Proxima B to help them measure various factors and search for potential biomarker molecules that could indicate the presence of life. Another critical factor affecting habitability is the presence of water. Despite the fact that Proxima B is in the habitable zone, it's still essential to determine if it has a sufficient level of water to be considered suitable for life. Water is a fundamental part of the equation, and researchers are looking for signs of liquid water on the planet's surface, whether it's oceans, lakes, or rivers. These pieces of evidence may be vital for assessing the potential for life on Proxima B. The presence of water in other forms, such as ice or vapor, is also considered, since water availability is crucial for supporting biological processes and is seen as a key characteristic of habitability. Proxima B raises further concerns about its environmental factors. Scientists need to examine other factors, such as temperature, pressure, and land formation, on Proxima B to analyze whether the planet's interior could be suitable for life to thrive. Extreme conditions, like intense heat or freezing cold, can make habitability difficult. Volcanic activity or seismic movement could also disrupt its suitability. However, it's crucial to note that Proxima B is likely tidally locked, meaning that one side of the planet stays in constant darkness while the other side is always illuminated by the star. The drastic temperature difference between the illuminated and dark sides could create extreme conditions that might affect the planet's habitability. These are just a few of the considerations that researchers are addressing in the search for habitable planets. Scientists are investigating the artificial composition of Proxima B to detect the presence of organic molecules, such as amino acids and other compounds essential for life. They will also be studying whether the planet receives enough energy from its star or other sources to fuel biological processes and support life. Despite all of this research, the question remains, does Proxima B truly have all the necessary ingredients to be considered a habitable planet? Is there substantial evidence for this? The discovery of Proxima B in 2016 was a significant milestone. Astronomers used the HARPS, High-Accuracy Radial Velocity Planet Searcher, device to detect the invisible gravitational pull of an exoplanet orbiting Proxima Centauri, our nearest star. This advanced precision spectrograph was designed specifically to catch exoplanets and is used at the La Silla Observatory in Chile. HARPS has been essential in the discovery of many exoplanets, including Proxima B. The HARPS device works by using the radial velocity method, also known as Doppler spectroscopy. Its purpose is to detect exoplanets by measuring the subtle shifts in the star's spectrum caused by the gravitational pull of an orbiting planet. These movements, called radial velocity or Doppler effect, happen as the star is gently tugged by the gravitational interaction with its planet. HARPS employs an optical fiber that collects light from the star and directs it to the internal spectrograph. Inside the spectrograph, the light is dispersed into its various wavelengths, allowing scientists to observe the star's spectrum. By studying these changes in the star's spectrum, astronomers can determine the star's radial velocity with exceptional accuracy, making it possible to detect even distant planets. HARPS uses advanced techniques, including temperature-controlled environments, to ensure that it produces highly precise measurements, eliminating factors that could interfere with the analysis. What's your take on Proxima B? Do you believe it is habitable, and do you think that, in the future, we might be able to move to this remarkable exoplanet? Let us know in the comments field. Thank you for watching the video. Be sure to like and subscribe, and I will see you in the NASA Explorer 1 test. The most distant human-made object in the universe is sending usable data back to Earth again. In the universe, we don't know how far it is, but we can measure it. Explorer 1, the famous space probe launched by NASA over 4.5 decades ago, has recently sent back a signal that has caused shockwaves through the scientific community. After traveling nearly 14 billion miles from Earth, Explorer 1 has made a discovery so significant that it has altered the course of its mission, now turning back toward our planet. But what exactly is this discovery? Could it be proof of extraterrestrial life, a massive anomaly, or something even more remarkable? In this exciting investigation, we will reveal these astonishing discoveries, as Explorer 1 just made an alarming discovery that caused it to unexpectedly return toward Earth. Records tell us that without certain celestial events aligning, the greatest rocket ever launched would never have left Earth. In this case, it was the alignment of the 4 largest planets in our solar system, which occurred around 60 years ago. These planets have been gradually aligning in a way that had remained unknown until then. The first person to realize its significance was Gary Flandreau, a doctoral student in aeronautics at the California Institute of Technology back in 1965. While space exploration was still in its early stages, working part-time at NASA's Jet Propulsion Laboratory in Pasadena, California, Flandreau was tasked with finding the most efficient way to send a space probe to Jupiter, or perhaps farther to Saturn, Uranus, or Neptune. Using just a pencil, he carefully plotted the orbital paths of these giant planets and made a fascinating discovery. In the late 1970s and early 80s, all 4 planets aligned in such a way that they could be visited in a single mission. This alignment meant that a spacecraft could use the gravitational pull of each planet to slingshot itself toward the next, drastically reducing travel time. Earth to Neptune, from 30 years to simply 12 years. Anyway, there was a trick. This planetary arrangement best happened once every 176 years. To take advantage of this exceptional open door, a rocket could need to be sent off through the mid-170s. NASA seized this once-in-a-blue-moon chance and developed space apparatus to make the experience. The rockets, Explorer 1 and Explorer 2, were sent on a first-rate undertaking to find the outer planets of our planetary system, thanks to the arrangement of the planets and the visionary estimations of Gary Flandreau. The launch of the twin spacecraft on September 5, 1977, marked something just incredible at a place known as Cape Canaveral in Florida. Explorer 1 set out on its epic adventure into space, lifted off by means of an intense rocket known as Titan 3E or Centaur. Only 15 days after, Explorer 2 was launched on August 20, 1977. Explorer 1 joined the grandiose experience, starting its journey into the vast universe, following a more limited direction. Their primary endeavor was to investigate the colossal gas giants in our solar system, including Jupiter and Saturn, along with their various moons. Yet these bold space explorers outperformed all expectations. They ventured far beyond, pushing the limits of exploration, visiting farther and longer than any other spacecraft in history. They broke various records on their moving odyssey. They've traveled beyond anything made by humans, sooner than wandering into an area referred to as interstellar space, a completely unfamiliar domain within our galaxy. These exploring spacecraft, Explorer 1 and Explorer 2, are now more than 12 billion miles away from us. Despite their enormous distance, they continue to astound researchers with the amazing discoveries they make. Most recently, they have made a discovery so unexpected that it has taken everyone by surprise. The Explorer twin spacecraft have achieved some truly remarkable accomplishments. More than 40 years ago, they studied the moons of Jupiter and Saturn. These moons, initially thought to be inert and flawed like our own moon, turned out to be vibrant worlds. Explorer 1 reached Jupiter in March 1979, just 546 days after its launch. Explorer 2, following a slightly different path, arrived in July of the same year. Every spacecraft was equipped with VidCon cameras, which used channels to capture full-color images. These cameras were designed to be incredibly durable, rotating through space at a rate 15 times slower than the hour hand of a clock. This ensured that the photos they captured were clear and sharp throughout their mission. The explorers took more than 33,000 photos of Jupiter and its moons, each revealing new and fascinating details. For example, Europa, one of Jupiter's 53 named moons, was found to have a fractured icy crust estimated to be more than 60 miles thick. As the rocket departed from the Jupiter system, they received a significant boost in speed of 35,700 miles per hour from a gravitational slingshot, a major maneuver that propelled them toward interstellar space. At Saturn, the explorers parted ways. Explorer 1 passed through Saturn's majestic rings, enduring thousands of impacts from small space debris before passing by Titan, a moon wrapped in an orange haze, traveling toward the north out of the plane of the planets. Explorer 2 continued its solo journey, reaching Uranus and Neptune in 1986. During its visit to Uranus, Explorer 2 discovered 10 new moons and introduced the planet to the list of worlds in our solar system with rings. However, Explorer 2's accomplishments were overshadowed by tragedy. Just 4 days after its closest approach to Uranus, the Space Shuttle Challenger tragically exploded shortly after liftoff, killing all 7 crew members, including Krista McAuliffe, a high school teacher from New Hampshire who was set to become the first civilian to travel into space. 3 years later, as Explorer 2 flew about 2,800 miles over Neptune's beautiful purplish-blue methane sky, it encountered the fastest winds recorded on any planet in our solar system, reaching speeds of up to 1,000 miles per hour. Neptune's largest moon, Triton, turned out to be an odd world with fountains spitting nitrogen into space. Explorer 2 captured this astonishing scene in a series of close-up photos. Following its visit to Neptune, Explorer 2 joined its sister spacecraft, Explorer 1, on an awe-inspiring journey into interstellar space as they ventured deeper into the unknown. The explorers encountered a mysterious boundary known as the heliopause, where the sun's influence gives way to the vast expanse of interstellar space. Explorer 1 crossed this boundary on August 25, 2012, becoming the first human-made object to enter interstellar space. Explorer 2 followed suit, crossing the heliopause on November 5, 2018. As they continue their journey into the unknown, the Explorer spacecraft carry with them a golden record containing sounds and images that capture the diversity of life and culture on Earth. This astronomical time capsule, created by a team led by astronomer Carl Sagan, is intended as a message to any extraterrestrials who may one day encounter the spacecraft. In like manner as Copernicus conveyed the heliocentric form, we might need to look once again at our monstrous figuring out a discourse in cosmology, alluded to as the fiasco. Modern cosmology has emerged. Neil deGrasse Tyson articulates that the James Webb finding has settled this conversation with material, innovative skill, breaking photo. So, what's this crisis, and how has the James Webb Space Telescope brought it to light? For those new, it's hard for antique clocks to investigate truly at it as a fiasco. At any rate, we are in a situation where we neglected to, as a matter of fact, recognize the age or size of the contemporary universe as they are related with a variable. Join us as we investigate the genuine edges of advanced modern science, where our insights are regularly tended to and abrupt openings are made. The favored model of cutting-edge modern cosmology, a smooth achievement all during the past 100 years, systems the universe's course, current development, current-day audits, and present status. Gravity intervened with the valuable asset of cutting-edge immense relativity essentially facilitates the universe's movement, recognizing its expansion and the strategy. Modern ultramodern great high-quality plans, components, and darkish power combine with darkish matter, conventional depend neutrinos, and photons. The universe began from the most recent tremendous bang around 13.8 billion years ago, followed by the helpful asset of cutting-edge expansion, causing density abscons. However, this model, not enduring with huge observational support, is now under an amplifying glass with the JWST. Cosmologists have a new gear that has been causing inconveniences in our norm model of the early universe. Before stars or, on the other hand, structures emerged, unbiased flotsam and jetsam followed 30,000 years after the Big Bang. Reionization lasted 550 million years, over time when most reductively the universe became ionized. The JWST presents cosmologists the ability to find more of the universe than was previously attainable, giving new investigations into the early universe. The typical model, recognized as the inflationary Big Bang or lambda CDM, has found different parts. Forefront, the universe yet conflicting proof has emerged, resulting in a crisis in cutting-edge cosmology. The calamity is pivotal. We don't consider much about the age, or the temporary status of the universe, and explicit techniques supply unique results. One tech approach used to measure the universe's age is the cosmic microwave background. Specialists jump into the universe's improvement records using mathematical exhibiting, based entirely on Einstein's state-of-the-art relativity theory. This speculation delivers the Friedman conditions, associating the universe's organization with its expansion rate at exceptional times. The astounding microwave background, CMB, extreme slight from the early days of the universe is an essential contraption in assessing its properties, pursuing a decision. Wary maps of the CMB, like those from the European Space Agency's Planck mission, need facts on dark energy, a critical member within the relentless universe. In spite of these issues, scientists use the Friedman conditions to estimate the universe's improvement rate and its ongoing age. Another technique to quantify the universe's age is by investigating detonating stars. While the cosmic microwave background gives an exact record of the universe's early development, seeing the universe's increase directly is possible through inconsistencies like type Ia supernovae, where a star dumps its air onto a close-by white dwarf, leading to an incredible blast. These supernovae act as solid benchmarks, noted as standard candles, permitting scientists to measure the universe's expansion rate at the hour of their explosion. This method, used in the last present-day years, was a significant part in finding dark energy, becoming an establishment in cosmological assessments. It is particularly useful for determining the Hubble constant, the rate of the universe's expansion since the Big Bang. However, late observations have shown errors within the expansion rate, suggesting possible dark powers at play. NASA has noticed an overwhelming discernment, expecting that the universe's expansion rate might be decreasing, which proposes a capacity to influence modern dark powers like dark matter. However, if the expansion rate picks up the pace, it may be ascribed to dark energy. The Hubble Space Telescope and outstanding units have estimated the evolving expansion rates through remarkable observation centers. Edwin Hubble, after whom the telescope is named, first proposed the expansion rate in 1929, initially interpreted as galaxies moving away from each other. It's now understood as the universe's expansion, but estimates from telescopes and methods remain difficult. Nonetheless, technological improvements and mistakes maintain uncertainties in estimating the universe's age and expansion rate. While these movements aim to answer fundamental questions, they also raise more weaknesses. One proposed explanation for the discrepancies involves potential flaws in cosmic microwave background measurements or variations in dark energy over time. Another possibility is the complexity of modern supernova modeling, which is crucial to uncertainties in their use as cosmological tools. The James Webb Space Telescope, while adding to our knowledge, has also further complicated cosmological issues, much like previous advancements, suggesting the need for a reassessment of modern scientific data. The Flamingo Project, a fundamental strain in the Virgo Consortium, addresses a multidisciplinary endeavor involving astrophysicists, cosmologists, computational researchers, and data excavators. This cooperative effort is focused on doing complex simulations that span the total galactic plan, from the early moments of the universe's establishment to the present day. These simulations are powered by cutting-edge calculations and numerical methodologies that embody our current understanding of major physical forces governing the universe. By comparing these simulations against an abundance of observational data, researchers can validate their models and gain insights into the hidden mechanisms driving galactic evolution. This ambitious project requires immense computational resources, and the Flamingo Project boasts modern high-performance computing teams and supercomputers to perform its simulations. These computational facilities allow scientists to simulate vast volumes of space at high resolution, allowing them to study the formation of galactic structures, star systems, and large-scale cosmic systems with remarkable precision. Funding for the Flamingo Project comes from diverse sources, including the European Research Council, national science and technology agencies, and academic research foundations. This financial support allows the team to get the right tools and resources to proceed with their computational goals.